Hey, Salim. Thanks for joining.
Good morning, Anu. How are you doing?
I'm doing well, thank you. We usually wait for a couple of minutes to get enough folks before we start. So, okay, we are at 8:03, so let's get started. Um, the first item I had was the Open Systems for AI um, meeting on Tuesday. I just want to make sure that everyone is set for their presentation, and they've got one person from the Workstream presenting. Rob Coyle shared the agenda with us, and it starts with um, I'm apparently giving an introduction, so I need to say something smart there. Um, then, Kevin, you're doing the bow for custom HPM, followed by Raghu for the virtual prototyping, then followed by George and Raghu for the profiling for HPCI applications. Shahab's going to do the optical, which is great. Shahab has more time now, which is worked out in our favor. A 10-minute break, and then we've got the systems work stream. And I know Rob is not going to make it, so either between Itai and Durgesh, I'm guessing one of you will present. And then we've got Patricia. It's a talk she gave at ISC, so she's going to talk a little bit about specialization needs for HPC, also for AI, and why chiplets then become essential part of an ingredient to this. Javad, you are next on the abundance of wires.
Yes.
Um, I, I know there's been so many emails you've probably had to catch up with. I just want to make sure you know you're you're on the agenda for Tuesday.
Yes, I'm aware. Thank you.
Excellent. And then the last one is CDX with David. Is everybody like all set? I know there's some kind of Rob made me aware that there is a Friday evening deadline to submit your slides, because I'm guessing they'd like to collate it all into one to make less hassle while presenting and switching presenters. So, Cliff, anything for us there?
No, I know. I think that's perfect. I'm very happy that we could fill a half day around all the work we're doing in packaging and silicon.
Okay, anyone else have any questions or issues? I don't
And
remember if Rob shared a template, but Cliff, do we just use an OCP template there?
sure, just use an OCP template. I don't think there was a particular template for this. I can double
Okay,
check with Rob.
I actually
sounds good.
checked.
Dave,
I checked with Rob, and the template to use is the contribution presentation template. If you give me one moment, I will post the link in the chat here.
Thank you, David.
oh my goodness, thank you, David. I knew there would be someone else who was way more rigorous about this than me. Thank you.
I know
So
a
for
few words to
everyone,
say about Global Summit if when we have time.
yes, we'll do the Global Summit next, and then I have Salem talking. So just everyone, there's David's posted on the chat. So everyone who's a presenter, sorry if I didn't even know there was a template. I think if you honestly aren't able to switch it to the last minute, I don't think the sky will fall on our heads. We will be perfectly fine because it is the material that's important. But if you get a chance to switch to this template that David shared, please do so. Okay, so we've covered topic number one. Second one was Global Summit. And Cliff, all yours.
Was that me? Yeah, okay, sure.
Yes.
So just let everyone know, we had just under 700 proposals for speaking, which was up from about 600 last year. So a little bit of growth. Thank heavens, not an enormous amount of growth because we still can't struggle to accommodate everybody. The good news is that the Chiplet community, open Chiplet economy was well represented. And Anu and Jawad should you be getting the information next week on the official track times assigned, but it should make everyone happy. And for the overall acceptance rate for the conference, it looks like we'll have a little over 50% of the proposals that can be accepted. That's assuming a 20 minute speaking slot, which includes 3 minutes of transition time per speaker. Some track chairs may pull 3 or 4 into a panel for 30 minutes, so that's just a theoretical around 50% acceptance rate. The other element around OCP Global Summit is the Innovation Village. Now we need to get that organized. I believe we have about 2 weeks until the deadline for the proposal for an innovation village. So Anu and Jawad, let's coordinate getting something in for that.
Yeah, okay. So sorry, Cliff, what was the deadline again for that?
Let me check the official one. It's about 2 weeks from now, but give me a minute. I will look it up. Well, why don't you continue along? I'll come back.
Okay, sounds good. I want to thank everyone who was able to get their abstracts in on time. For those who couldn't get their abstracts in on time and you still have something, of value to add, reach out to Javad and me. We figure out the day's program, and we do want to showcase things we're doing for the community in terms of chipping away at this chiplet ecosystem. So if you did not get a chance, we're still open to looking at how to finagle things around to make sure we put our best selves forward in a manner of speaking. So thanks to everyone who could make it, and everybody. I mean, life sometimes gets in the way, and you're not able to do it by that. And our life is guided by far too many deadlines at this point. But let's make sure we get all the valid pieces into the program. I don't
Yes.
have anything else for Global Summit right now, Cliff. I think other than there are dates when we'll get to figure out what the program is, and Javad and I will work through uh, what needs to, what the flow should be, and invited speakers, and if we would definitely like to have at least, I would like to have at least a panel in the morning and one in the afternoon, because those really perk up an audience, and usually pretty good stuff comes out of it. So if folks have ideas for anything like that, I'd appreciate them, and speakers who, to be honest, like there's times I feel there are so many conferences on chiplets and packaging um, that sometimes I feel it's an overload and there's a repeat factor in a lot of places. Speakers tend to say the same thing simply because they don't have the bandwidth to go prepare a new PowerPoint, and so I'm not, blaming anyone for it. I just would like ours to be slightly different, where uh, it's not as prepared, maybe some of the panelists. Just saying some fresh blood would be nice, I think. I finished my rambling, Cliff.
Okay, Anu, so I looked it up for everyone. It's July the 11th. That is the closing date for the Innovation Village. We should put in a coordinated proposal,
Okay,
like we did
sounds
last year.
good. Yep. Okay. Anything else from anyone? Any questions before we move to our presenter? Excellent. Salim, it's all yours. Please introduce yourself, and thank you for agreeing to come on this call. I know that you have a conflict with the Workstream that you originally joined, and so we're happy to have you here. All yours.
Thanks, Anu. Let me know when you can see the slides.
Yes, we can see
Okay.
that.
Okay, so my name is Salim Abdelnader. I'm a principal engineer, part of Intel. I work for the Intel Foundry Services, and I'm an IP tech lead in that organization. So I know what I've done is I have a couple of presentations. One of them that I gave in GoMac Tech 2024. There is another one that I gave in 2025. Actually, the 2025, there are a couple of them. One of them related to the open chiplet ecosystem related to testing, kind of addressing all the testing challenges. And the other one is about a phased approach. So I would like to start with what we presented in 2024. And I'm doing the same thing that you said that we shouldn't do, which is recycling the slides. So I'm recycling.
No, I'm sorry, but I haven't
It's
seen
okay.
it. So it's brand
Okay.
new.
Yeah. Okay. Perfect. So let's go ahead and kind of go to the slides in here. And please interrupt me if you have any question. I think kind of the intent of this one to have this one as interactive. So kind of in this presentation, I'm going to be talking about the challenges and the solutions for an open chiplet ecosystem. But kind of the first few slides, this is pretty much kind of the typical introduction to heterogeneous computing, benefits, and of course, I think like all of us that are part of this discussion are very aware that advanced packaging is really becoming more critical to meet the everlasting demand of electronic product. So if we look at the development in advanced packaging, both 2.5D and 3D IC, they're answering the call for more processing power and bandwidth. So definitely in industry, we see a rise in heterogeneous computing and a rapid growth of a chiplet market, as we're showing in these two graphs. One thing, there is a lot of buzz around open chiplet integration, about open chiplet economy, and actually the possibilities are being expanded by chiplet creating opportunities for new market. So in GoMac Tech, of course, we focused on the Mac customers. We focused on DoD and the aerospace. So, but it doesn't matter. When you look at chiplet systems, there are two broad categories of chiplet systems to come together. One of them is the homogeneous integration, and the other one is the heterogeneous integration. So the heterogeneous integration, what it does, it involves combining a chiplet that are optimized potentially in different process nodes and that have different system function in a single ICs. And of course, when we talk about homogeneous integration, this is really the disaggregation of an SoC by combining two or more chips into one. So there are, I put in here the heterogeneous integration benefit. It applies to the homogeneous. There are a bunch of benefits driving industry to move towards the heterogeneous integration. So this is from a reduced NRE cost to shorter time to market to flexible IP reuse, and also optimized chiplet that is fabricated in a different node. So for example, an IO chiplet does not have to be on the bleeding edge technology. It can be designed on a mature technology. So again, I mean, the focus here is pretty much advanced packaging is one of the main enabler, but also besides the advanced packaging is the interconnect techniques. The die-to-die IP and standardization that is happening is fueling the wide adoption of chiplets. So this is kind of the first jargon. I'm not going to spend that much time on the slides, but the trade-offs here, and I'll share the slides with Anu if she wants to post it. But what we enumerated here is the trade-off from a swap perspective. So from performance, security, manufacturing, cost. So it's the whole size, watt, and power advantage. And one thing that we're trying to drive within the MAG, the DoD, and the aerospace kind of customers, and they're very interested in that. It's the application reuse, which is key in the market chiplet availability in an open market for use. And what they are interested in, they're interested in commercial chiplet that they can be used for DoD. DoD wants to engage in the SOTA. So if you look in the SOTA microelectronic, but they want to go beyond the utilization of COTS chips. So this is kind of where we were trying to do the driving force, and that's the reason we presented it in the GOMAC in 2024 and 2025. So from kind of the chiplet enablement, and I know I'm going to be talking about the UCIe, but I'll focus on that. But whatever happens with the UCIe as a die-to-die, kind of the same challenges, potentially solutions will apply to any other interface, such as a bunch of wire. But if I start with the nirvana for chiplet ecosystem, kind of it's an open chiplet market or an open economy chiplet. And the idea behind this is to have an off-the-shelf chiplet that can be used to build a custom design or leverage external chiplet in order to reduce the development time. So to achieve this, there are several technical and business challenges that need to be addressed. Maybe today we're going to be focusing on the technical challenges, but there are a lot of business challenges that I'm going to touch on. I mean, there is absolutely no solution presented in this one, but this is something that we're seeing at Intel from an adoption, from an open chiplet ecosystem. You can address some of the technical challenges is how you address the business barrier that we might see. So again, one pillar of a chiplet ecosystem enablement is a common die-to-die interface. We cannot talk about an open chiplet ecosystem if every company, they have their own IP kind of proprietary interface. Intel, for example, I mean, I've been with Intel for 30 years. There are maybe 4 or 5 different die-to-die interface from an MDFI, multiple of them that would not allow an open chiplet ecosystem. So this is where standardized chiplet interfaces are really crucial to chiplet reusable. And also, just like in order to be able to enable a Lego-like mix and match kind of capability, I think if you look at UCIe, and I'm going to focus here, it's both UCIe and bunch of wires. Kind of the essence of them lies in this strategy. So again, I'll be talking more about the UCIe from an interoperability and compatibility, but I think the same thing will apply to even other die-to-die interfaces. So
sorry, I have a quick
Sure.
question. This is the
Sure. Yes.
So if a customer is going to Intel Foundry, right now EMIB and Foros both are supported, or for external customer it's only one of them?
So for external customer, both. So the definitely the EMIB is the solution for the 2.5D. So this is pretty much the parallel to the CoWoS. But then within Foveros, this is the 3D IC. There are multiple different Foveros technology that is offered. So right now, as an Intel Foundry, we do both offer the 2.5D, which is the EMIB bridge. And even within that EMIB bridge, there are multiple different flavors of an EMIB bridge, one of them with TSV, one of them without TSV. But then also from a Faveros, there is the Faveros Omni, the Faveros Direct. Those are all different techniques for a 3D IC. So we do offer both a 2.5D, kind of an interposer or a silicon bridge-based technique, or a 3D IC based on the Favero technology.
Okay, great. So EMIB has a interposer also?
So EMIB, actually, we don't call it an interposer.
Yeah.
CoWoS is an interposer. EMIB, we call it a bridge, but EMIB will have a TSV. So we have an EMIB-T that we offer, and this is, for example, the HBM4 will have to use an EMIB-T, a UCIe 48, a UCIe 64 gigabit per second, will have to use the EMIB-T technology. This is the through silicon via. But then if we look at, we have a development on a UCIe 16 gig with an IP vendor. They used an EMIB, not a TSV based, which is just an EMIB 1.7.
Okay, thank you. This was very helpful. Thank you.
Thanks. So from a die to die, again, like I'm going to focus on this one. Kind of this presentation is from Intel, so it's expected to focus on the UCIe. But again, I would like to drive this point. A UCIe ecosystem challenges are the same as a bunch of file chiplet ecosystem challenges. Actually, the fact of having two potentially die to die make the interoperability and the compatibility of the different chiplets that are available potentially another challenge. I mean, actually, internally, we looked at a combo, a UCIe bunch of wire UCIe AIB, because don't forget, Intel drove the AIB interface within the RAMP program of the government. There is a lot of AIB-based chiplet that was developed. So the first thing that we faced with the UCIe adoption is we're going to be ending up with two different chiplet libraries, one of them based on AIB and the other one based on the UCIe. So the same things like will apply when we have a bunch of chiplet that are based on a bunch of wire and others that are based on UCIe. But from the Universal Chiplet Interconnect Express, which is the UCIe, this one was announced in, I think it's like March 2022. And there are different founding members from ASE, AMD, ARM, Google, Intel, Meta, Microsoft, Qualcomm, Samsung, and TSMC. But then over 100 companies have joined the consortium within the last, kind of the first 6 months of the incorporation announcement of the UCIe. So this is, I mean, I think kind of like one of the things that we looked at it. It's and then also the feedback that we got from multiple IP vendor. There is a really evidence of the broad industry support and also the critical mass that is needed to create and sustain a viable chiplet kind of industry ecosystem. So from chiplet ecosystem challenges, and I borrowed, I think I like this one from AMD. But if you look at the chiplet interoperability, it requires, first of all, specifying the mechanical, the thermal, the electrical, and also the functional details of the chiplet. So in addition to the protocol and looking at the electrical and the physical specific interoperability, standard integration model for all function for chiplets, they need to be addressed. And this is including software, firmware, security, manageability, debug, test, power, thermal, RAS, as we're showing in this figure. So there are multiple, I mean, each one have its own challenges. Potentially this one, when we look at the protocol, electrical and physical, and the reasons like this one is green, because the specific interface, like when you look at the UCIe standard, it was trying to address some of the issues with that are seen in order to make from a die-to-die perspective, but there are more. So besides the kind of the standard integration and technical challenges, there are business barriers that needs to be addressed. And this is kind of logistics. How do you mix different foundries? So for example, if you have a chip that is coming from Intel Foundry, a chip that is coming from TSMC or Samsung, there are logistics in mixing foundries. And then how do you do, who owns the system level test? System level test, or PPV, this is at the system of chips level. And if a failure occurred, how besides, I mean, how we debug, who is liable in some of the failures? So there is a bunch of additional challenges that needs to be addressed from system level test, from KJD, kind of the known good die. Those are all kind of additional challenges that makes interoperability or compatibility kind of much more complex than resolving the some of the technical issues that we might see. So I like this slide because this one, it shows the components. I mean, there are different components of interoperability. So this is typically a system of chip. I have two different dies that are connected, and I think the interoperability of chiplet is better visualized by looking at the different component of a disaggregated design. So looking at the die-to-die I/O, so this is part of the OSI, the physical layer. Looking at the die-to-die protocols, and this is the OSI data link to the presentation layer. And then the other thing is you have to look at the SoC construction. So the system of chips, you have to look at the reset, you have to look at the initialization, the access of the different registers, you have to look at security. And this is kind of another component, which is the application layer. And the other one is the chiplet form factor. You look at the die size, you look at the bump location, you look at the power delivery, you look at the thermal characteristics. So each item is really a component that making chiplet interoperability and compatibility a major challenge in enabling what we're referring to as an open economy or an open chiplet ecosystem. And if you look at the UCIe spec, I'm not very versed on the bunch of wire, but I'm sure bunch of wire is doing the same thing. If you look at the UCIe standard, it's addressing this. It's addressing the die-to-die I/O. So this is where I draw a line on potentially where different IP vendors or different design team are designing a die-to-die interface based on the standard. They can guarantee a certain interoperability that happened. And actually, we had a really good test case with Intel and Synopsys. So Synopsys designed an N3 UCIe without any engagement with Intel. And of course, they looked at the UCIe. It was based on UCIe 1.0, and they did it on N3 technology. Intel was designing a UCIe on an Intel 3 design. Again, like this is without any interaction with Synopsys, and they were able to pair. So there is a test chip that we called Pike Creek, and Pike Creek had the Synopsys TSMC N3 test chip paired with the Intel UCIe Intel 3. And they were able to interrupt from electrical standpoint. And I want to focus, it's only the electrical. So this is, I think, kind of it was a good proof of concept that if we follow the spec as is and enforce it, potentially you will be able to have interoperability, even though that there is not that collaboration between the different IP vendors or the different design houses. So it was kind of a good proof of concept, how standardization is really key in potentially enabling some sort of interoperability between the chiplet. But then when it comes to the die-to-die protocol, when it comes to the SoC construction, the chiplet form factor, these are added kind of challenges. And in the next slides, I want to just potentially go at a high level for some of these items and focus on potentially some of the challenges that we see from these particular component for chiplet interoperability.
Salim, just
Sure.
a question. When you talk about the Intel and Synopsys engagement, I think that's really very positive to know that both sides independently followed those spec,
Mhm.
and they managed to communicate electrically. Um, I'm assuming there was some kind of initial handshake, or we're going to use standard packaging, both sides. Um, the pitches, I guess, between 110 and 130. There's an initial set of parameters which probably had a handshake, or are you saying it was totally independent?
Actually, it was totally independent, but luckily Synopsys used I mean, of course. So what we ended up doing, that test chip, the Pike Creek test chip, was not a CoWoS based. It was, I'm
Right.
sorry, yeah, it was an EMIB based. But Synopsys, what they developed their N3, they developed it for a CoWoS based design, not for the EMIB. But if we looked at the bump pitch, exactly what you mentioned, I mean, the first thing we have to look at is, are we talking about organic or advanced packages? So these
Mhm.
are both UCIe-A. The other one is we looked at the micro bump pitch, and then also designing the EMIB bridge with the different bump pitch, different bump arrangement. So there are certain things that we had to do a little bit of hand holding and
Right.
swizzling that happened at the EMA bridge. So yeah, that happened later on, but from the initial design, from the initial IP design, it was kind of independently. The minute we started putting the interposer or the silicon bridge, there is a lot
Mhm.
of interaction that happened between both Synopsys and Cadence for the Pike Creek.
Okay. And both sides agreed to what the protocol would be, or it didn't get all the way to the protocol layer?
Oh, that's a great question. It did not get to the protocol layer because the protocol, we couldn't, the two, it's only an electrical interoperability.
Got
It
it.
was not protocol interoperability, unfortunately.
Understood. Thank
But,
you.
that's a great point. That's a great segue into kind of like some of the challenges, because, and this is what I tried to do. I took the typical, this is from the standard, kind of a typical UCIe, and I mapped a UCIe to a typical interface stack. What we end up with, because when we talk about interoperability and compatibility, to me, it's really a big word. It's easy to talk about like an open chiplet ecosystem, but what we end up with when you look at the interface stack layer, when you look at kind of a specific die-to-die interface, what we end up with is a complex system chassis compatibility. So the electrical, the protocol, the mechanical, the device management, the test, the security, all these are certain issues that potentially kind of a physical channel you will be able to interface, but at the other level, there is no way that you're going to be interface. So these are kind of examples that I want to show in the next slide. And this is, I'm going to be focusing on only selective examples, because I want to leave potentially 5 minutes to go to what we've done in 2025 on kind of the phased approach that we're seeing when we talk about an open chiplet ecosystem. Are we really there? So I just want to potentially leave the audience with the poster that we've done in the 2025 GOMAC Tech. But briefly, let's go through some of the slides to kind of understand more some of the challenges. So one of them is the die-to-die protocol. If you look at the UCIe, and I think like it is the same thing for the bunch of wire, it is really a layered architecture. So the UCIe specify a raw PHY sublayer, which can be used by itself via a streaming interface for custom usage. So for example, like when you want to try to disaggregate large chip and connecting chiplet via potentially any proprietary protocol, a lot of customers are going that route. They're going through the raw streaming mode. But on top of this, what the UCIe did, they defined a die-to-die adapter flow control unit. This is what we refer to as the FLIT. And this one has its own cyclic redundancy check. It has its own replay mechanism, which can also support different customer protocol. So the UCIe, what they've done, they specified a standard way to map industry standard, which is the PCIe and the CXL protocol layer on top of the PHY. So this approach, it does provide a well-established interoperability model for connecting, for example, processors or accelerators. But I mean, we're seeing that this is not the way that customers would like to use the UCIe. They do not want to use it in a PCIe and the CXL. The streaming mode in UCIe, one of the things, and this is based on a lot of the IP vendors that deals with multiple customers, they're saying like the most of the customers, they're looking at the UCIe usage in a streaming mode. And this is mainly because of latency, because of power, because of area, because also the flexibility to use a user-defined protocol to be transmitted using the UCIe. And this is kind of like where we see potentially a certain challenge. AXI is, I mean, a lot of customers, they were very interested in using the UCIe in a streaming mode, but then using the AXI as a bridge. And for Chiplet that are using streaming mode and using the AXI bridge, in order to be able to interrupt, this needs to have a common address space configuration. So, I mean, we are in dire need of a standard AXI mapping onto UCIe. So this is really needed instead for each chiplet to use their own mapping. Because if you have a chiplet A, you pair it with chiplet B, each one will use their own mapping from an AXI perspective. That's it. There is no way that you'll be able to interrupt. So if you look at ARM has this standardization of the multi-die, and it's a chai-based system using the UCIe streaming. I mean, till now, I haven't seen an ARM standardized multi-die AXI-based system using the UCIe. So it is a certain gap. We tried to take it to the consortium. The consortium did not want to address anything related to the fabric mode. So this is something that we had multiple conversation with ARM related to standardization of a multi-die AXI-based system, similar to what they've done for the standardization of a multi-die chai-based system using the UCIe. So this is potentially one of the challenges that customer will use when they want to use the typical AXI bridge as a fabric.
So I have a comment on that.
Sure.
This is Dipesh again. When I was at NVIDIA, I was representing NVIDIA and UCIe, and NVIDIA is close to ARM. So we were the ones who pushed Chai over UCIe, right, as native mode. But ARM was against AXI because they want to transition away from AXI to Chai, including the smaller accelerators. So there is a lot of AXI ecosystem, but they don't want to build that. They just want to focus on CHI.
Yeah, I agree with you. I agree 100% with you. Even the conversation, we know what is the rationale behind ARM standardizing the multi-die chai, but yeah, I agree with you. I know that there is a rationale behind them from the stuff. We tried to push them as well, and I think we had NVIDIA as part of the call in order to the discussions like for the ARM, but we did not get anywhere from them. But
even in our one-on-ones, we used to meet them weekly, right? I mean, NVIDIA architects had wrote 60% of the spec C2C, but they were not budging.
Yeah, I mean, I do have an AXI-based spec that they've developed, but this is a year and a half ago or 2 years. But as of now,
they don't want to pursue it.
Yeah, they don't want to pursue it. So which kind of makes it a little bit of challenging for customers that they do not want to switch to a chai-based system. So we'll see where that leads. But that's a major factor that needs to be kind of incorporated from.
Yeah, I agree with you. And there are others who are asking for it as well, because the AXI ecosystem is very big.
Exactly. Agree with you 100% on that one. So the other challenge, I think, like we talked about it, is the chiplet form factor. And within the chiplet form factor, there are multiple things, I think, and I'll talk about the bump locations. So the bump map, definitely it's key in a chiplet compatibility and interoperability. So the UCIe, when you look at the spec and you look at the bump map, it's only a recommendation. I mean, and even when we deal with the IP vendors, they look at the spec, and sometimes some of them comply to the bump map that exists in the standard. Sometimes it's not. And they mention like this is only a recommendation in the spec, and this is for both standard and advanced package. So the focus kind of like on recommendation, that means there is room for optimization. We've seen a lot of the IP vendors provide us with the UCIe with a different bump map that does not match the consortium standard. But if you look as a counterpart, so this is how the advanced package, it's strongly recommended. So they focus on this is only a recommendation. We'll provide you a recommendation, but you can do. But if you look at how the HPM spec is, when you look at the JDEC, even for the HPM4, the bump map is a rule. That means for the HPM DRAM, all the HPM DRAM vendor will have to comply to the bump map that is specified as part of the JDEC. And most SoC team, what they do is they map whatever the HPM DRAM, they mirror it, and that is a key in the chiplet pairing flexibility. Because if you end up with different IP from different design team or different IP vendors that have completely different bump map, the first issue that you will see is how you're going to compensate that. Within the EMA bridge, there is potentially some room in order to do some staggered routing, but then like kind of the approach in here is you have to match this. I mean, there is a little bit room in an EMA bridge to jog, but not that much. So kind of a one-to-one bump map mapping between the different dies that you're pairing is really, in essence, in a chiplet interoperability. And I think what Anu mentioned, this is kind of the physical layer. You're dealing with different, this is of course the UCIe will never interrupt with the UCIe-S. There are two distinct options, and this is one kind of thing that you need to address. The other one is how IP vendors do their design. I mean, I think like what I'm showing here is how Synopsys does. The PLL is part of an external macro. Cadence, what they do, the PLL is in each one. So even when you pair, where you place the macro, when you pair, for example, an IP coming from Synopsys and an IP coming from Cadence, you have to look at all the different configuration that might happen, and also the abutment that will potentially create different configuration. So there are multiple challenges. So even though the IP vendors or the IP design team will comply 100% to the spec, but the spec does not specify where you put your PLL. It's up to you how you design your different modules and how you abut them together, and then how those will be paired. So definitely an alignment on the die-to-die configuration, it's really key when we talk about the chiplet ecosystem, because from a DoD perspective, they want a chiplet library, the chiplet that's already available. For example, a compute chiplet, an ADC chiplet, an IO chiplet, and they want to use it as is. But then kind of an alignment on the die-to-die configuration, besides the fact, is this advanced, is this a standard? It's the bump arrangement, the characteristics, the physical orientation as well. I mean, most of the chiplet, is this an east-west orientation? Is this a north-south orientation? So does that mean in order to do an open chiplet ecosystem, you provide a compute chiplet? One will need it as an east-west orientation. The other one will need it as both east-west, north-south. So even an orientation of the decision of what kind of chiplet needs to be developed in order to guarantee an open chiplet ecosystem. present some of the kind of the challenges as well. The other one is the application layer. So this is where it is key, because it's easy to look at the spec, but then you have to look at the SoC construction. So and this is where it takes us to the phased approach. So when you start to do a system of chip, and this is what happened actually with Synopsys, when we took the for the Pike Creek, the Synopsys M3, the Intel 3, we have to look at the SoC construction. This one will require a lot of collaboration between the companies, for example, in this case, using the UCIe interface, in order to ensure kind of the interoperability. And this is potentially a business limitation as well, because when you talk about an open chiplet ecosystem, potentially you're impeded by legal and business interest as well. So this is where you're mixing different chiplet from different foundries becomes an issue, but that's the business one. But from an SoC construction, there is still a lot of need in order to have a common customer requirement and guidelines towards a reusable off-the-shelf UCIe solution for the ecosystem. And I'm going to put it in this one. I'm not going to go into details. This is an example when we try to use two different dies on an advanced packaging and looking at all the different issues from an interoperability standpoint. And this one shows you, I mean, this is the standard, how they define it. This is potentially the interoperability issues that you can see. So from a reset domain, from initialization, the sideband communications. So when you have two dies, kind of the end-to-end sideband communication, how we address that at the adapter level, how they want to do it at the SoC level. The bandwidth throttling, of course, the standard require certain link clocks in order to do that. The implementation is very flexible. That's the spec, but you can use that. The other one is the link initialization for HVM. Which one participate as part of the protocol layer during the reset bring up. Sometimes in the SoC construction, both dies that you're pairing will need to have a similar link initialization for your high volume manufacturing test. The other one is the debug data transport. How do you send your test data over the UCIe sideband? The UCIe spec did not define it, so there is no dedicated mechanism to transport that data. And this one, I think, will require, once you do that and you want to transport data for debug purposes for a system of chip, both dies that you're pairing, you have to have a specific recommendation on how you trace messages can be interpreted by either the die A or the die B. So this one's like, again, really, it's a more detail on the SoC construction and some subset of issues that we've seen when we try to pair two UCIe from different sources. I think like if you get the UCIe from the same source, it's much easier. So for example, if you have two dies using a Synopsys IP, it's much easier from interoperability. But if you have a die A that is designed by Intel or has, for example, a Cadence IP, the interoperability at the SoC construction becomes an issue. There were more. I know it's like we're kind of 9 minutes, but I wanted to talk about the die-to-die power management, because from an industry standardized chiplet power management, it's pretty much a new paradigm. For UCIe, we have seen some challenges. If you look at the UCIe sideband to the SoC level, it's undefined. The sideband run at 800 megahertz. There is no inter-die management protocol defined. Of course, the consortium ended up using the MCTP, which is the Management Component Transport Protocol. So this is the one that will provide the fundamental structure of communication between the platform management components. So this is where you have to go beyond the typical electrical and physical implementation, even the die-to-die power management and how the two dies need to communicate with each other, and making sure that is part of the MCTP protocol component as well for some of the die-to-die management. And the last slide that I wanted to show, this is related to thermal and power, because different chiplet might have different material. So when we talk about an open chiplet ecosystem, let's say you have a chiplet coming from company A, another chiplet coming from chiplet B, potentially they use completely different material. And that will impact your thermal and power consideration for the whole system of chip. So there are different floor planning potentially, and these different floor planning will have different thermal map. So from chiplet interoperability, you will need to consider flexibility in the chiplet placement. And I'm showing in here different chiplet placement and which one will provide you with the best thermal map. So, but then in your design, you have to make sure that you incorporate that as part of the design. So you have to consider flexibility in the chiplet placement, the network design, and also the interconnect routing. Because when you have chiplet next to each other, you can have a certain routing. The minute you put them far from each other, that's a completely different routing that you have to incorporate in the die in order to guarantee an open chiplet usage for this one. So potentially a better thermal dissipation capability might be achieved when specific chiplet are not required to be placed close to each other. But with that, if this is an advanced packaging and you have kind of an interconnect between these two, you have to make sure that you incorporate that as part of your design. Slide 17, I'm not going to focus on. Last GoMac Tech, we did a whole thing on testability. Testability and repair is a major challenge when it comes to interoperability. But this is kind of pretty much an example. If the spec does not dictate how the interface best should happen, where the pattern generation and check, it provides you, and we've seen this, I've seen this one in a real product, when we had two different chiplet A interpreted the interface best as the pattern generation and checker happens at the same die. Another one interpreted that the interface best, the pattern checker happens in die 1, and the other one happens in die 2. So this is where any disaggregation, test, and repair, it really needs to be enforced throughout the supply chain. Otherwise, you're going to be ending up with two dies. First of all, you're not going to be able to test them because of the interface best. And if this is advanced and you need to do a repair, there is no way that you can repair if the capability is not there. So this is kind of another challenges that, and with the UCIe consortium, I know we drove what kind of pattern generation and checker needs to be part of the die in order to be able to guarantee kind of an interface best. I know we have only 5 minutes, but I just wanted to kind of end up on this one because there are, I think what we see, and this is part of a lot of the discussion that happened within the OCP, and summarizes kind of the different challenges. There are multiple discipline and domain. So kind of the die-to-die IO is one of them, EDA, manufacturing, production. So these are all kind of the different issues that potentially we see that. And I think like within the OCP, when I was active in part of the business workflow, I mean, we looked at it from different angle. We looked at it from standards, which one that has to be driven with standards. We look at tool and references. We looked at the production support. So this is where the business workflow, you have the system of chip integration, you have the system of chip design, and you have the chiplet interconnect. This is kind of specifically looking at the die-to-die part, the models that needs to be delivered. This is part of the CDXL initiative within OCP. So so with that, I mean, I just want to flash. Am I sharing this, Anu? Can you see
Yes.
the? Yeah. So I just wanted to kind of potentially stop in here in where we see the different phases of an open chiplet ecosystem. And we put it as here, industry experimentation, customized collaboration, and a
Okay,
full.
hold on.
Sure.
Salim, we're seeing the slide that's called establishing a new open chiplet economy. So if you're sharing something else,
Let me do a new share.
it might be on a different screen of yours.
Yeah, it might be. It's a different presentation. So can you see it now?
I see 3 phases of open chiplet ecosystem here.
Yeah, this is the one that I wanted to kind of end
Okay.
this conversation with. So this is where we see the 3 phases of an open chiplet ecosystem. So pretty much this is the nirvana. This is the full chiplet adoption. And definitely this is working. And I mean, if the team is interested, I can come and present on all the different standards that we see that are evolving in order to drive the full open chiplet ecosystem. We really believe we're in a customized collaboration in here. Industry experimentation happened. If you look at NVIDIA, if you look at AMD, if you look at Intel, a lot of them they've done. I mean, if you look at kind of designing their product based on the chiplet architecture, is not something new, but it's within the same company, so you have better control. So that happened. The customized collaboration, we see a lot of that. And I think kind of like the one that I mentioned about the Pike Creek is an example of a customized collaboration. What happened between Alpha Wave, ARM, that's another initiative. The Cadence unveiling kind of a few months ago, the ARM-based chiplet ecosystem. This is a collaboration that happened. So this is where we are. We see that customized collaboration is very successful in providing a chiplet that can be used within the company, within the different company. The full open chiplet adoption, I think this is where we want to be. And this is where there is kind of really a call for having standards pushing for beyond the die-to-die interfaces. So I know that's what I wanted to cover today.
Thank you so much, Salim. And you talked about Nirvana. Do you know when we'll reach stage 3 Nirvana?
I mean, of course, we wanted it to be 2 years ago, but I think it's going to take take a lot of time to do. I mean, there are again technical challenges that needs to be addressed. So realistically, an open chiplet adoption where you can have a Lego-like mix and match, I think we're still away from that. But with the customized collaboration, I think this is going to be a stepping stone. And we might be in here for a while, similar to, I think, 2.5D and 3D. We thought the 2.5D is a stepping stone to 3D. Look at us. We're still in a 2.5D, and it's not a stepping stone. So potentially we will stay in a customized collaboration. There is a whole initiative within the DoD to do a chiplet library, but we're focusing on potentially 4 to 5 chiplet to start with. So that's what's going to happen. I think we have to walk before we start running for in this concept.
Agreed. Any questions? Cash, I thought you had a question. I know
yeah, I still see things like BIST and known good die. I mean, you talked about the business barriers. I mean, ignoring the fact that the standards need to change, right? So that also is something that we've seen as a big barrier, right?
Agree.
Particularly with advanced packaging, where you can't probe all the PHYs, right? So so that's caused us to, do some extra work that we weren't anticipating, frankly, right? So
I agree.
I think it's actually a bigger issue that nobody talks about.
Yeah, no, I agree. I mean, we talk a lot. Yeah, we talk a lot about the technical issues that potentially can resolve. Right. Those business barrier might be hindering, and we've seen it with we've seen it with Pike Creek, and Pike Creek, right. We've seen it is because the die is from TSMC. So there was a lot of impending legal issues that we need to really navigate, even to announce the Pike Creek initiative.
I did have one question. Have you guys done a study on the testability at wafer level where you don't test the phi fully, right? Because once you get to 20 micron and below pitch, and only test fully at the package level, what you know, with things like infant mortality and stuff like that.
Yeah, we've done that. We have the SDX, and I can present this one because that's the singulated die-based approach. So I think if the team is interested, either in this forum or I know the Wednesday forum, now it's more flexible because we're ending a tape out. So potentially I'll come back and join the Wednesday meeting. Definitely we can bring the testability topic into discussion and then talk about the singulated die testing.
Yeah, no, I think that would be of actually interest to a lot more people than just at that forum. So we might pull you back in at this one, Salam. So
sounds good.
Thank you so much.
Yeah, no, I think
Thanks,
exactly. I think that'd be a really important one, and we have great interest in that. Thank you.
Agreed.
Thanks, Salam.
Thank you, Salam. Thanks, everyone. Have a great weekend.
Thanks.
Bye.